Thank you. My name is André Izidoro. I'm a postdoctoral fellow at the São Paulo State University in a city called Guaratinguetá. So I hope everybody remembers this name at the end of the talk. And then I'm going to talk a little bit about the solar system in the context of exoplanets. So I changed the title and a little bit of the angle of the talk because I thought that would be more exciting for this audience than the previous plan. So everybody's familiar with this plot that shows everything that we know about exoplanets. So we have here masses and period. So maybe you don't have the masses for this planets detected by transit, but then we can use a mass-radius relationship and then to calculate them. So this is just approximation plot. So and you can plot the solar system planets over this plot. So and then you can see very prominent islands in these regions. So that you call these planets as hot super Earths, these ones as hot Jupiters, and these guys over here, Jupiter-like planets. And so this is the solar system. The solar system is quite nice. You have 4 terrestrial planets, 4 giant planets. The innermost ones are mostly silicate bodies, and the outermost ones has water and volatiles. So how do we understand the solar system in the context of exoplanets? So let's first look at how super Earths are. What kind of information you have about the super Earths? Super Earth systems, they typically come in multiple planet systems. You have more than 1 planet per system, and they are extremely compact. Their orbits are extremely compact. They are really close to the star. So here is a plot showing the TRAPPIST-1 system, and the inner solar system, it's that region here. I mean, if you put it on a scale, the TRAPPIST-1 system in the solar system, that's what it should look like. So you can see how close to the star this system is. And there's another nice Kepler systems, that the Kepler-11 systems. So if you put the solar system here, so all these maybe 6 planets, they should be inside the orbit of Venus. So that shows that these systems are extremely compact. So what kind of statistics do we have for these super Earth systems? They are observed in about 30 to 50% of the solar-type stars. They come in multi-planet systems, and they have very compact orbits. So the solar system does not have something like this. Very low. So let's give another look on the orbital configuration of giant planets in extrasolar systems. So here this plot shows semi-major axis versus the centricity of gas giant exoplanets. So the blue points here are the solar system planets, and each one of these triangles is one exoplanet. So what we can see clearly is that these giant exoplanets have very high eccentricities. So this is quite different from what we see in the solar system. So these are very 2 main differences that we see for the solar system and the exoplanets. So you have super Earths that are extremely compact, extremely close to the star, or do you have these crazy systems with giant planets in very centric orbits? So let's first look at how super Earths form. So one of the promising ideas, maybe the most promising one, is that super Earths forms by migration. So here you have a disk, a protoplanetary disk, the star is in the center, and you're going to put a 5 Earth mass planet in this disk. So this is what happened. The disk interact gravitationally with the gas and launch these wakes. And then eventually it migrates. Typically, migrations is inwards. So if you have a big enough planet forming far out from the star, it can migrate inwards. So we think that physics should be universal. A lot of this should be universal. So we expect a few things to happen in protoplanetary disks. So we expect that the inner regions should be hot, and the outer regions should be cold. So in the inner regions, it should be silicates, in the outer region should be basically ice. And the between here, you can mark the snow line that we heard about this morning. So because ice grains are bigger and they stick better to each other in the outer part of the disk, we expect to form much easier, larger planets in the outer part than in the inner part. So we should expect to see some kind of division between always having water-poor bodies in the inner region of the solar system and water-rich bodies in the other regions. But there is one thing that changes this ordering That's migration. If you have a planet coming from the outer part to the inner regions, sun, then you don't have this order anymore. So let's see how super Earths may form. This is a simulation. Show one example of super Earth's migration. Here you have a system of a few bodies that has masses of a few Earth masses. There's a protoplanetary disk. So the color shows the masses. The sun is here, and you have eccentricity. So these bodies, at the simulation that I showed before, they will interact with the disk. They will exchange angular momentum and migrate. And so that's what happened. So they start to migrate, and eventually, all of them, or almost all of them, hit the inner edge of the disk. So that might be the way that we form the systems closing super Earths. So here at the end, you have 1, 2, 3, 4, 5, 6 planets inside 0.5 AU. That's look like similar to what we get from observations. So then, after a few million years, the gas dissipates, and then you have a system of super Earths. How do we explain this eccentricity of the extrasolar gas giants? So we know that giant planets, they should form in the disk if they have a very massive envelope, because they have to get this envelope from the disk. And then they should keep in low eccentric orbits during the time the disk is still around. So here's a hydro simulation showing 2 planets in the disk. So you can see that during the time that the disk is still around, they keep it typically very circular orbits. But this is quite different from what we see today. So but after the gas dispersal, after there is no more damping or something that can keep these orbs cold enough, these planets can interact with each other and become dynamically stable. Here you have just a cartoon show what might happen. You can start with a system that have very circular orbits, and then because of long-term gravitational interaction, they may start to crossing orbits, and eventually one of them is ejected from the system. And the guy that survives has a very eccentric orbit. So here is a simulation showing this kind of evolution. We have 2 giant planets. They start with hopefully circular orbits, and then they're going to cross orbits eventually, and one of them is going to be ejected. So let's see. Now, this guy gets ejected, and this one survives in a very eccentric orbit. So most of the extrasolar giant planets that we observe might have been through this phase. So they might form in circular orbits, as we expect, from the gas disk phase, and later they evolve, become eccentric. So the question is, how the solar system fits in this context? This is an event like this happen also in the solar system. And the answer is yes. So we believe the solar system had a dynamical instability. It's not sure when it exactly happened, if it was late or if it was early. So here, just an example. You can imagine the giant planets, they form in a much more compact configuration, what we call resonant configuration, like this. And then the interaction of these bodies with the primordial Kuiper belt, and even with the terrestrial planets or the building blocks of the terrestrial planets, they go through a phase of stability, and then boom, they reach their point orbits. They start in a very compact configuration with very circular orbits, or almost circular orbits, and then they evolve to a more eccentric one. Here's a simulation, a real simulation showing this evolution. So we have here the sun, the 4 gas giants in the solar system, the 4 giant planets, and you have a cold Kuiper belt. So they start with very circular orbits, eccentricity smaller than 10 to minus 2, something like this. And then they interact with this disk, and eventually there is instability. And they get more eccentric orbs, the orbs that they have today. But why these orbs are not so eccentric as those of the extrasolar giant planets? And the reason is because we are lucky. So here's a plot showing the eccentricities of planets in different systems. And these 2 blue dots shows what happened to the solar systems in terms of when Jupiter has a close encounter with Saturn and when Jupiter does not have. So the upper point here shows what could have happened to the solar system if Jupiter and Saturn had a close encounter during this phase of stability. But luckily, we do not have. So they keep very low eccentric orbits. So that's the reason that why the solar system is so different from the extrasolar gas giants. We are lucky, and Jupiter and Saturn, they avoid a close encounter during this phase of instability. So if you look at the planet distributions or planetary sense that you have, we see this abundance. These planets here that has sizes between 1 and about 3 Earth masses, 2.8 Earth Earth radii, they are pretty frequent. And these guys here, they are very rare. So we know from statistics that most of stars have planets. So maybe 50% or a little bit more of the stars has gas giants, like Jupiter. They are rare. So 85%, or maybe less, does not have gas giants. So for these systems that has gas giants, that corresponds to about 50% of the stars that we observe, only 10% corresponds to solar system-like systems. 90% of them are systems of very eccentric gas giants. For the system that does not have gas giants, we have what? Super Earths. So maybe 30 to 50% or maybe even more of the Sun-like type stars has systems that has super Earths. So these are solar system-like. This should be the hungry gas giants, and this is the hot super Earth. How the solar system fits in this context? These hot super Earths, they are observed in 30, maybe 50%, maybe even more of all solar type stars. Why don't have one in the solar system? What happened here? Why Jupiter and Saturn has such low eccentric orbits? Why does Earth exist? This is the new point, the next steps of this talk. So here you have a movie that we already saw before. One of the slides, you have the Sun, you have a system of super Earths, have the disk, and the super Earth should migrate inwards. And then you have a system closing super Earths in the inner regions. But what happened if the first of the innermost super Earth of the system becomes Jupiter? And then the super Earths that they are behind Jupiter cannot pass it. They get blocked. And that's what happened. So here's a simulation. So here we promote the innermost super Earth of the system to be Jupiter. So we have Jupiter, have super Earths beyond Jupiter, and have disk of gas, and everybody here is interacting with the disk of gas and migrating. So that's what happened. Jupiter starts to migrate, but Jupiter migrates much slowly than the super Earths because it's migrating the type 2 mode. And eventually, there's a pilot of super Earths beyond Jupiter. So they cannot cross Jupiter's orbit because they are capturing resonance. And then we stop the simulation eventually at 5 million years. So in the case of the solar system, we don't have only Jupiter. We have Jupiter and Saturn. And then you put Jupiter and Saturn in the systems and a bunch of super Earths after them. And because Jupiter and Saturn has a specific mass ratio, they can avoid migration. So you can assume that they are not migrating here, different from the previous case. So they are fixed. And these guys are migrating as expected. So that's what happened. They migrate inwards, some of them get scattered, and eventually form a system of a few planets. And if you wait long enough, they're gonna become unstable again. But the gas is still around. They can migrate back to near the giant planets. And in the end, you're gonna have only 2 ice giants. That's basically what we get in the solar system. I think this is gonna happen at 3 million years, if I remember well. So just later a little bit more. So there's a stability about to happen. Boom. At the end, you have something that looks like Jupiter, Saturn, Uranus, and Neptune. And there's no super Earth crossing beyond Jupiter's orbit. So during this process of blocking the super Earths beyond Saturn, the gas giants might explain why you don't have this size of planets in the solar system. So this size of planets, they are not seen in the solar system. So they're basically planets with about 5 Earth masses. So maybe the reason for that is because Jupiter blocked the super Earths beyond them, Jupiter and Saturn, and this body had about 5 Earth mass in size, but they collide to make Uranus and Neptune. And that's why we get these planets. Okay, we might not believe in this. So then I give you a prediction. We can test it observationally. So if this is true, you should expect an anti-correlation between the presence of giant planets and super Earths. If you see a system with many close-in super Earths, like this, you should not see a giant planet far out. If you see a system with a giant planet, so you should not see many super Earths inside, and they should be maybe beyond the giant planet. So of course, we cannot expect that this is 100% true. Because imagine that Jupiter is not the innermost super Earth of the system, but maybe the second innermost one. So then the innermost one should migrate inwards. Maybe the second, third innermost one becomes Jupiter. So, but if you can test this observationally, you can learn a lot about how super Earths form, how gas giants form, and even about planet formation. So, but what if there's no Jupiter inside in the solar system to block the ice giants? Then that's what might happen. Okay. So we have here a super Earth, just a single one. We're going to assume that you just have a single one. And you have a disk of planetary ambius and planetesimals in the terrestrial region. And you mark here the habitable zone of the system. So, and the super Earths are going to migrate inwards. And that's what happened when they cross the terrestrial zone. Eventually, when they reach the inner edge of the disk, we remove the super Earth from the simulation. So we just care what happened here in this gray region. So after the gas disk dissipates, there's basically nothing to form in the terrestrial zone. Of course, this is just one possible evolution for the super Earth. If super Earths migrate really, really fast, then maybe you can avoid this kind of outcome. But here you cannot form an Earth-like planet, of course. So Earth's formation might be a consequence of Jupiter avoiding the invasion of the inner solar system by super Earths, Uranus and Neptune. What if Jupiter and Saturn were hungry gas giants, as we saw before for most of the exoplanets? So if they look like this, a very centric orbit. So here's so maybe we can put this, make fun. So here we have a simulation with 3 gas giants, and we have material in the terrestrial region and material beyond the orbit of the giant planets. And you're going to let this system evolve to see what happens. This kind of simulation is successful in reproducing the centricities of the giant planets that we observe. So eventually these systems will become dynamically stable, and we're going to see the outcome or the consequence for the terrestrial region. So now one of these planets is going to have close encounter with each other, like here, and then boom. So if you look again, what happened in the terrestrial region, there's nothing to form a terrestrial planet. So the solar system, how atypical is the solar system? We can make some speculation about that. So if you observe, we're going to see that maybe 10%, maybe a little bit less, 5%, a few percent of the stars that we see should be like G-type stars, like our sun. 50% of the systems have no super Earth, because we don't want a super Earth crossing the terrestrial zone and destroying everything. So 10% of the systems, only 10%, has planets like Jupiter and Saturn, like cold orbits, and distant orbits, and only 10% of the giant planets has low eccentricities and inclination. If you multiply out this, you get the probability of having something like the solar system could be 1 in 2000. So that's where I stop.